So let's start by thinking about the state space of our design. Designs today contain a lot of flip-flops, typically far more flip-flops than the flip-flops you can see on this slide, but suffice it to say a lot of registers in the design. That would include flip-flops, latches, memories. So let's shrink down those flip-flops a little bit and just consider what we have here, which is, I can't remember, 100 or so flip-flops. Even with 100 or so flip-flops, and there's probably more than 100 flip-flops on this slide, that represents a massive state space. If we've got n flip-flops in our design, then we've got n state bits. So each of the numbers here is n bits wide. And if we were to try to write out the complete state space of our design, then we'd end up here with a column of n-bit numbers. So there's n bits in each of these numbers, 1 bit for each of the flip-flops in our design, 2 to the n states in our design altogether. So if we were to write out this column of numbers in binary or decimal notation, whatever we wanted, we'd end up with a massive column. And in fact, the number of distinct values in this column would already be significantly larger than the estimated number of atoms in the visible universe. So we're talking about an astronomical state space, even for the relatively small number of flip-flops you can see on this slide. And of course, your designs have a massively larger number of flip-flops than this. So the point I'm trying to make here is that with any reasonable sized design, the state space is astronomical. The number of different states that our design can be in at any one instant in time is truly astronomical, not even beginning to think about the fact that the state space of the design evolves over time, which of course it does. So let's think how we'd simulate a design. So we start off by putting the design into a reset state. We apply our reset signals, and that forces the design into a unique starting point. And we then start simulating, and as we simulate, the design evolves into multiple possible states. So as we step forward clock cycle by clock cycle, the number of possible states that the design could be in explodes to soon reach an astronomical number. But of course, for simulation, we pick a particular state in each cycle. So as simulation advances, simulation is advancing through a specific state. And a complete simulation run just traces out one very specific path through the astronomical space of possible states of our design. And we then run another simulation, and another simulation, and another simulation. And by the time we've run multiple simulations, we've still barely scratched the surface of the possible range of states that our design could be in. But even that being said, we've still achieved something very, very valuable, because when we run a simulation, what we've done is to identify one specific use case in which our design actually works properly, and that's tremendously valuable. And I'm calling that a golden thread. So simulation traces out golden threads through the state space of the design. Each golden thread is one specific path through the state space of our design in which our simulation works, assuming that we haven't got any assertion violations or no checkers are fired. And this is very, very valuable. We've demonstrated that our design can, in some cases at least, work properly and do useful things. But of course, we've barely scratched the surface of the state space, and we certainly haven't proven or verified that our design is going to be correct under all states. We've only verified the design for certain specific golden threads. So simulation has certain weaknesses and certain strengths. There's a couple of key weaknesses for simulation. Simulation requires us to define input stimulus, and then we'll only simulate what we choose to test. So simulation will only exercise the state space of the design according to the input stimulus. And since defining input stimulus is very often a manual or semi-manual process, we're really vulnerable to human error here. We might simply not have tested our design under the cases that really matter, and we won't necessarily know that. And also, simulation can barely scratch the surface of the state space of the design, and that's a significant weakness for simulation. And of course, when I say simulation, that weakness would apply equally for emulation or for FPGA prototyping. But simulation also has some enormous strengths. Simulation can demonstrate that the design works end to end for specific cases, and of course those strengths also apply to emulation and prototyping. Simulation, emulation and prototyping allow us to demonstrate the existence of golden threads where our design actually works end to end. And simulation is also relatively fail-safe. Of course, simulators could have bugs, but it would be extremely unusual if a simulator bug hid a design bug. So having a design bug and a simulator bug that cancelled each other out, we got a false positive, is theoretically possible, but extremely unlikely to happen in practice. So having spoken a little about simulation, let's contrast that with formal and model checking. With formal model checking or property checking, the state space of our design is represented symbolically. It's not fully enumerated. So a formal tool doesn't go through the states of our design one by one. It represents the states of our design using a mathematical equation, if you like, representing the state of the design symbolically. So we can represent all of the states that our design could possibly be in without actually needing to go through and enumerate the states one by one. The states can be manipulated using mathematical proofs. For formal model checking, we start by defining target states, and those target states are typically going to be represented by assertions or by cover directives. And what we do with formal proof is then to try to establish that those target states can be reached, and when they're reached that nothing goes wrong. So let's look at that with an assertion. A typical target state might be a state that would cause an assertion to fail or fire. So in this case, our assertion is saying that in every clock cycle, whenever request is true, then grant has to be true in the following clock cycle. So this particular assertion would fail or fire if ever we had a request being true, followed by a state in which grant was 0. So what a formal tool is trying to do is to find a sequence of states through the state space of our design that's going to cause this assertion to fail or fire. So the formal tool represents this target state of a request being 1 followed by a grant being 0, and then attempts to find a sequence of states through the state space of our design that would cause our assertion to fail or fire. And it does that mathematically, analytically. So the formal tool never has to explicitly represent all of the states of our design one by one. And that allows the formal tool to explore astronomically large numbers of states without having to explicitly consider those states one by one. In fact, a formal tool can quite comfortably complete proofs where the size of the state space of the design exceeds the number of atoms in the universe. Out of the question for simulation, but entirely possible for a formal tool. So when we're done, we end up with a formal tool having explored what I'm calling a golden nugget. So with formal, we identify certain target states, we then run our proofs, and when those proofs have completed, we've identified certain areas within our design where we've exhaustively, unequivocally proved certain properties of the design. I'm calling these golden nuggets because they represent very, very significant areas of the state space of the design. A golden nugget could represent an astronomically large number of states, but it's not the entire state. It's typically not an end-to-end thing. Typically, it's just representing a local area of the state space of the design where we know we're good. We know the property is proven. We know we've been able to satisfy a particular cover directive or prove a particular assertion. So contrasting simulation with formal, simulation and emulation suffer from a time explosion. With simulation or emulation, there just isn't long enough to simulate every case. But what we can do is demonstrate specific end-to-end use cases, and that's very, very valuable. Formal, on the other hand, suffers a state explosion. Typically, we don't have either CPU time or memory enough to completely explore the state space of the design. But what we can do is to identify golden nuggets, local areas within the state space of the design where we have explored the state space.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of John's webinar, Formal Verification for Non-Specialists, whenever you want, by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.